All right, so in this video, we are going to discuss about the RC phase shift oscillator. Right, so as the name suggests, the RC phase shift oscillator would probably have the combination of resistors and capacitors. So first thing is that this type of oscillators is used in low frequency circuits, probably the circuits like audio circuits and all that. So you can use this type of oscillators in those circuits. The other thing important thing is that the overall phase shift, the phase shift of the op amp is 180-degree, which means it's a inverting output, right? So in order to counter that, you need to provide a beta or the feedback so that this 180 is countered, right? So that you can justify the condition, which is the angle of or the phase angle of A alpha beta should be equal to 0 or 360-degree, right? So the circuit has to work in a way that the beta value should provide the counter 180-degree or adds 180-degree of the phase shift so that you will eventually have a zero phase shift at the output, right? All right, so in order to understand how the combination of R and C would work, let's first try to understand the basic RC circuit. So that's my R, that's my C, that's my Vin, and this is my output over here. That's V out, right? So this is very simple high pass filter, if you remember from previous tutorials, or you can say it's a phase lead circuit. So let's try to figure out the transfer function of this circuit. So that would be V out over V in, which should be equal to R divided by R minus JXC. And if I try to just manipulate and reduce this into some more significant form so that I can understand the phase shift, so that will become as 1 minus J over omega C R, right? So as you can see over here, the phase shift value would be equal to 0 minus tangent inverse of minus 1 over omega C R, right? Alright, so once we try to further reduce it, the phase shift value turns out to be just tangent inverse of 1 over omega CR. And we know omega C, 1 over omega C is what? It's nothing but it's XC, right? So I can say that the phase shift for the circuit would be tangent inverse XC over R. So for this circuit, if we apply the circuit, the phase shift that we can get is tangent inverse XC over R, right? Now just think about the maximum and minimum value that you can achieve from this circuit. If I try to reduce the value of resistor very low and I try to increase the XC value to a very high value, I would probably have something like, for example, 1000 over 1, right? So let me try to do tangent inverse of 1000 or 10,000 over 1. So I'm getting an answer of 89.9, which means that the phase shift value can reach a maximum value of 90 degrees. Maximum, or it can reach to a very low value of 0 degrees, right? So if we even if we try to reduce the resistors to a very low value, we will eventually get to an extent to the 90-degree, but practically it is not possible to make this like resistor 0. So we won't be able to reach to the exact 90-degree, but yes, to an extent we can reach to that 90-degree part. Right, so since we cannot reduce this R too much, like 1 or 100 or 10. So what do we need to do is we need to make or build the circuit in the cascaded form. I'm gonna go and clean this up. So what do we have earlier was a C and R circuit. Now I'm gonna cascade this to one more C and one more R, right? So the first thing over here is that I have to reach to a value of 180-degree, right? The phase shift by this first circuit was approximately 89, which I can say it's a 90 degree. When I cascade it with another CRRC circuit, that would be again another 89, which is approximately 90 degrees, right? The combined phase shift, the combined phase shift of both circuits now turn out to be somewhat near to 180 degrees, which is required by the beta or the feedback circuit. Now, honestly, like let's be all like we discussed that we cannot reduce the value of R to such a low value. So the best possible way to construct a practical circuit is usually that we have three cascaded systems. What would happen is that the first one would provide a phase shift of somewhat 60 degrees. The second one should provide another 60 degree, and the third one should provide another 60 degree, right? So we can actually have some like manageable value of resistor. Like we know that it was tangent inverse XC over R, right? So we can just manage that to 60 degree as an answer with some value of resistor. So this is how the design of the circuit would look like, that we have the capacitors and resistors combination going over there. All right. Now, after all of this knowledge and information, let us try to build our RC-based oscillator circuit. So we have an operational amplifier, right? We have a positive terminal which is grounded. We have a negative terminal which has a R1 resistor, and we have a feedback resistor. Over here, let's say that's RF. And this whole circuit will give a phase shift of 180 degrees. So counter phase shift from this output, I'm going to add a C, a resistor, capacitor, resistor, capacitor, resistor. And that's my V out. And I'm going to draw it from here till this endpoint, right? So this is the diagram, or the circuit diagram, for my RC phase shift oscillator, right? Over here, this whole region is basically providing a 180 degree phase shift, right? So in order to counter that phase shift, I have designed this whole region, which will provide another 180 degree phase shift. So overall phase shift at the output will turn out to be 360 degree or 0 degrees, right? So there will be no phase shift and it will work as an oscillator. All right, so there are a few important formulas that you would know. They have a derivation, but I'm not going to drive them, but I'm going to just quickly write it down so that you can understand and use them. The frequency, if you want to design at a very specific frequency, the formula for frequency for RC phase shift oscillators is 1 over 2 pi root of 6 RC. I know there would be concern in your mind, but from where do you get the root 6? You can probably get a lot of videos and notes available for the derivation of this root 6. Uh, it's just about providing the circuit over here and then trying to carry out the nodal and loop analysis over here to actually figure out the value of the constant over there. The other thing that you should know, that's one of the formulas. The other thing that you should know is the RF over RI, which is over here, the combination of the feedback, and it should turns out to be 29. So the gain of this op amp turns out to be somewhat around 29, right? Because of uh the loss of signal, or the uh attenuation of signal over here in this part of the circuit. So it turns out to be 29, so you have to have a gain of 29. These two formulas are very important going forward in designing your circuit. Okay, with that being said, let us try to do one quick question for the RC phase shift circuit. The question says design RC phase shift oscillator that oscillates at a frequency of 10 kilohertz, right? So first of all, you know that your circuit diagram is again the same. right? So your circuit diagram is same. You have capacitors over here, you have resistors over here, you have uh, system over there, right? So you have to design your filter at right. So you have to design your filter at the frequency of 10 kilohertz, right? The formula that I'm going to use is frequency is equals to 1 over 2 pi 6 RC. Now again, like always said, you can fix the value of capacitance. I'm going to assume that capacitance is 0.1 microfarads. So my frequency is 10 into 10 power 3 because it's a kilohertz. 1 divided by 2 pi root 6. Resistor, I don't know that. And for capacitor, I'm going to use 0.1 microfarads, right? When I try to solve it, the value for resistance that turns out to be is 64.97 ohms. So all of these resistors are basically of 64.97 ohms, and all of these capacitors are basically of 0.1 microfarads, right? All right, so the next thing is that we need to figure out our RF and RI for the circuit. You already know that RF over RI should be equal to 29, right? So in order to make the circuit stable, Ri should be greater than R. Otherwise, the loading effect will happen on the circuit. So we don't want to do that. So that's why we keep the Ri value to be higher than R. Probably it's suggested that you take 10 times of the R value. So now your Ri value would turn out to be 10 times of the R, which means it is 649.7 ohms. I just multiplied that with a 10 over there, right? So that would be your Ri value. On the basis of that, you can actually figure out your RF value, which would be 29 multiplied by 649.7 ohms. And that turns out to be 18842.46 ohms, right? So that's the value for the feedback resistor over there. So yeah, on the basis of these values, if you implement that circuit, you would eventually have no phase shift because the phase shift would be cancelled or 360-degree opposite, which is again the same. And you know your value for the feedback, you know your value for the input resistors, and you know all the value for the capacitance and the resistors. So this is how you have designed a RC phase shift oscillator at a frequency of 10 kilohertz.